Welcome back, everyone, for day 2 of section 4.2. We're going to formalize what we were talking about in day 1 and talk about tests for extreme values of functions. So what you're looking at here are two functions, f of x. One of them is increasing to the left of c and decreasing to the right, and one is doing just the opposite. So what you notice here is that f prime would be positive, then f prime is 0, and then f prime goes negative. To the right, where there's a relative minimum on that graph, f prime is negative, then f prime is 0, and then f prime is positive. So what we can say is f prime changes positive to negative at a relative max. Similarly, we can say f prime changes negative to positive at a relative minimum. You need to be careful about saying f prime is 0 at a maximum or minimum. That may or may not be true. So, for example, in the graphs of f below, to the left of where f prime is 0, so here f prime is 0, f prime is positive, then f prime goes to 0, but then f prime goes positive again. That is not considered a relative maximum. Similarly, in the next graph to the right, f prime is negative, then f prime is 0, then f prime is negative again. So f prime is 0 at that location where where I'll highlight it here and here, but f prime does not change sign. It goes to 0 and then goes back up above 0, or goes to 0 and then goes back down below 0. So we can formalize this. It's called the first derivative test for relative extremes. And if c is a critical point of a continuous function, remember that is where the derivative is 0 or undefined. If f prime changes from positive to negative, then f has a relative max at that value of x. If f prime changes from negative to positive, then f has a relative minimum at that value. If f prime does not change sign from negative to positive or from positive to negative at c, then f does not have a relative extreme at c. So first derivative test, just some common sense rules to remember about using derivatives to find max and mins. Okay, so let's use that to do an example here. Cable revenue. What we have is a model for a cable revenue for 26 weeks after it begins its sales campaign, and that function is given by r of x, and x is the number of weeks since the TW cable began its new sales campaign. And part A says locate the point at which TW cable's revenue peaked during this 26-week interval. Okay, so what we're going to do is we're going to find r prime of x, and then we're going to graph r prime of x, and we're going to look for where r prime of x changes from positive to negative, because that would mean that the slope goes from positive to 0 to negative for the function r, and therefore we would have a local maximum. So the first thing we do is we find r prime of x, and r prime of x is going to be negative 12x cubed plus 480x squared minus 6,000x plus 24,000. And we are going to plot that on Desmos, r prime of x, and find where r prime of x changes from positive to negative. Okay, so if you remember from pre-calculus, this is a cubic function, which means it will definitely cross the x. It's an odd degree function, which means it'll definitely cross the x-axis at least once. I do have the function in right now. You're not seeing it, so you're going to have to play around with the window. And if you play around with the window a little bit, you will see that R prime goes from positive to 0 to negative at x equal 10. That is not a relative maximum or minimum. Okay, that's a flat spot on the graph, but of R of x, but it's not a max or min. At R equal 20, you can see that the graph changes from positive to negative. Now, it might be a little bit hard to see that it actually changes from positive to negative. If I zoom out a whole bunch, you can start seeing the slope of that. So now you can see that it changes from positive to negative as we move from left to right. So what we know is R of x has a relative maximum at x equal 20. So I want to remind you of a nice thing you can do on your calculator if you now need to evaluate the function R of x at x equal 10. If you put that function in y1 or y2 or whatever, and you go back to the home screen, you can say alpha and the trace key y1 of 10, so put parentheses, 10, and it will evaluate that function for you. So what we have is when at week 10, after they implemented their campaign, their marketing campaign or advertising campaign, they reached a relative maximum of 70,000. Sorry, I made a mistake there. I said at 10, it should be at 20. At 10, we had a flat spot in the graph, and we'll go back and look at that again. So alpha trace y1 of 20, and that evaluates the function for us. And there we go. There's the relative maximum of 80,000. So if we go back and we look at this graph, we'll see at week 10 they had a maximum, they had a value of 70,000 revenue dollars, but at week 20, you'll notice at week 20, which kind of makes sense in here, somewhere between 78 and about $77,000, they reached a maximum there. So just to recap, we set this equal to 0. Well, we didn't set it equal to 0. We found where R prime changes positive to negative at x equal 20. Part B says, at what other point is R prime of x equal to 0? Part B, R prime of x is equal to 0 at x equal 10. Explain what happened to TW Cable's revenue at this point. It reached a plateau. Hopefully I'm spelling this right. Not sure about that, but just to illustrate what's going on there, at x equal 10, what we had is we had this function that came up, flattened out, and then continued to increase, and then at 20 is where it reached its maximum. All right, the next example we want to deal with is a case where the first derivative test fails us. Well, it doesn't really fail us, it doesn't apply is really the case. So we have this function h of x, it's a piecewise function, and there's a graph of it down here, and h of x is in blue, and h prime of x is in black, and I'm going to highlight that. So h prime of x is like this, and then like this, and then open circle, and then h of x is like this and like this. Okay, and what I want you to notice is that h of x has a relative max here. It's actually also an absolute max, but we'll talk more about that in the next section. And you will also notice that h prime of x changes positive to negative here. Okay, well, there's a problem with that. And the problem with that is, well, not so much with that, but there's a problem with the first derivative test there. It says Suppose C is a critical point of a continuous function. So the assumption there is that you have a continuous function. If you have a continuous function, like we did in our last example, and R prime, for example, goes positive to negative, then we know we have a maximum. Okay? In this case, R prime goes positive to negative, but the first derivative test doesn't apply. So we have to be careful about using the first derivative test because it doesn't always apply. So how does that play out in this example? So here is h of x, and the derivative h prime of x, it's not really clearly labeled, h prime of x, so 2 times 0.5x squared is x, and the derivative of negative 2x plus 16 is negative 2. So what we have to do is we have to think about where the function h of x transitions from one part or piece to another, and that's at x equal 2. So if you evaluate the derivative h prime of 2, you get, when it's less than 2, you get 2, and when h prime of 2, when x is greater than 2, and by that I mean slightly greater, then you're going to get negative 2. So we do have a sign change of the derivative there, positive to negative. So as long as the function is defined there, we do have that relative maximum. So this point right here is the location of our relative maximum. What we're going to do next is we're going to finish up trying to graph some possible functions from information about the derivative of the function. So here's an example. F prime of x is negative for x less than 1. So what does that tell us? That tells us that the function is decreasing. F prime of x is greater than 0 or positive for x greater than 1. So that tells us the function is increasing, and it tells us that f prime of 1, the derivative is 0. So at x equal 1, the derivative is 0. So what we know is we have a function that kind of goes like this, and this is less than 1, this is at 1, and this is when x is greater than 1. And a possible graph of that is right here. So here's x equal 1, derivative's negative, derivative 0, derivative positive. Notice I said a possible graph of that. That actually could be something that goes like this as well. It could be shifted upward, still meets those conditions. So there's not a unique solution for this. It did also say that f is continuous in this example, so watch out for clues like that. In this next example, g satisfies the condition. G prime of x is equal to 0 for x less than 1. So what do we have? We have the function is flat or horizontal. G prime of x is positive for x greater than 1. So we know that the function is increasing for x greater than 1. And g of 1 is equal to 2. So we know we go through the point 1, 2. So a possible solution for that would be, here is the flat portion of our graph for x less than 1. Here is the derivative being positive for x greater than 1. So we have a positive slope, could be any slope. And we know we include the point 1, 2, so that's why this point here gets shaded, because it's the point 1, 2 on our function.